September C++ meetup. I think that this is by far largest meetup that we had in past 12 months, sorry. And I think majority of people here are now, as I heard, from H-Tech company. Correct me if I'm wrong.
Can you raise your hands?
Well, please raise your hands. Yes.
Welcome.
Welcome. You choose the right thing to do in Wednesday afternoon. Okay. So I would like to present Ivica as our today's speakers, and you enjoyed the talk. I already seen this talk on CPCon last year. Probably Ivica made some modifications, but it's a very interesting topic for this month. So welcome, enjoy, and that's it.
Okay.
Without further ado.
Thank you. Hello. So the name of the talk is the performance price of virtual functions, and I'm not sure how should I call it, because we're going to investigate how virtual functions and how C++ generally interacts with hardware. So this is more geared toward hardware engineers, but also includes, of course, a lot of C++. You don't have to have any special background for this. You can just enjoy and relax and follow the topic. So let me just give you a quick introduction to virtual functions, because some of you might not know how these things works, but I guess most of you know. So the basic premise of C++ is in virtual functions is that they enable flexibility. So you have a base class, you have derived class. Derived class can override the behavior of the base class, and this is what virtual functions enable. They allow a lot of flexibility. For example, implementing them in C would be quite a problem. And virtual functions are actually a basic component of object-oriented programming. So you cannot imagine modern software development without virtual functions. Now, virtual functions have this, how should I say, they have this bad reputation of being slow. But the question is, why are they slow? Or how they are slow? What is the reason of their slowness? Is it that really important? And some people say, like, the modern computers, they're really fast. We don't care about that. But sometimes you do care. And in today's talk, we're going to investigate exactly that. Now, the performance of virtual functions, and you will see, as you will see in this topic, is not a straightforward thing. So it actually depends on many parameters, which are not necessarily related to virtual functions, but these kind of problems will appear in an environment, is more common to appear in an environment where you're using virtual functions. Okay, first a short introduction how virtual functions are implemented by the compiler. So C++ standard does not mandate how virtual functions are implemented. You can implement it any way you like, but most compilers implement it in a similar way. So you see here this. We have an array of instruments. Instrument is a base class, and this is an array of base objects. But each of these points to a different object. And for example, this object is wind instrument. This one is percussion. This one is string. Then this one is brass. So what happens with virtual functions? So instrument has three methods: play, what, and adjust. But how do we know? For wind, we call certain implementation of play, and for percussion, we call another implementation of play. And this needs to be decided at runtime, not at compile time. So the address of the virtual function is not known at compile time, and it is dispatched at runtime. So each instance. So how does that work? It works like this. We have a virtual table, which is per type, not per instance. So there is one virtual table for all wind objects, one virtual table for all percussion objects, and so on. And inside each instance, so each instance has a virtual pointer, which points to that table corresponding to that type. So we have a wind objects, and it has a virtual pointer, which is 4 bytes or 8 bytes on 64-bit architectures, which points to virtual table that has entry 0, which is play, entry 1, which is what, and entry 2, which is adjust. And this is how things work. Now, what happens if when we want to run, when we want to execute? So we have an object. Let's say we are processing an object. We want to call method adjust, but we don't know its address. We need to know its address. And how do we get that its address? We go to the virtual pointer, which is typically hidden member of the class. You can see it in debugger. You cannot see it regularly. It's a hidden member of the class. We go to the pointer table. We know that the adjust method is at entry 2. And we go to the entry 2, and this is the address of our function. When we have address, it's trivial to call it. So this is how function calls. Any questions? No questions. Okay, it's not complicated. So the initial analysis says that virtual functions are more expensive than non-virtual. The reason is because for each object, you need to do this. Go to virtual pointer, find the address, call that address. So you have one additional step, the reference, and so on. Virtual tables are typically in the cache because they're used often and they're not big. So we don't have that problem of missing caches unless we have like thousands of different instances. In that case, that would be a problem. For non-virtual functions, the compiler knows the exact address at the compile time. Okay, so it doesn't need to do any of these things. It can just load the address, actually load the value of function address to a program counter and just jump to it, and that's it. Just a single jump instruction, the simplest case, not always. Okay, so what I did here is I did some small analysis. I have a vector of 20 million objects, all of them are same type. And I have 20 million calls to the virtual functions, virtual versus 20 million calls to the non-virtual function. And what I get is, if I have a short and fast function, virtual function is 153 milliseconds and non-virtual is 126 milliseconds. And if you have a long and slow function, virtual function is 32,000 milliseconds and non-virtual 31.8, which is almost in the error of measurement. So we can say like the initial analysis says, well, virtual functions are not that slow. But remember, we have the objects of the same type. There is only one type. Okay, so now you would say, okay, this is not that bad. We can use this, but is that all to the story? And the answer is no. So let's see what else are the parts that we're missing here. So when you're using virtual functions, how do you store your objects? You need to access them through references or pointers. From the compiler point of view, difference between reference and pointers are really small, essentially. Pointers can be null, or reference cannot. Now, what happens is that, what's the problem with the vector of pointers? The vector itself is a continuous piece of memory, and you can access these pointers are next to one another. But the objects, the pointers are pointing to certain objects in memory, and they're not necessarily neighboring in memory. What that means is that every time you dereference the pointer, you get some random memory address, and this random memory address actually can be a problem from the memory subsystem point of view. From the memory, because you're targeting random addresses which not necessarily have to be in cache, this increases fragmentation and slows down the access. And yeah, so look at this. So we have std vector of base class, and this is another std vector of base class. I have two layouts here. One I called optimal layout. Why is it optimal? Because I have neighboring pointers point to the neighboring objects in memory. So I child class 1, child class 1, child class 2, and so on. So neighboring, and this is the optimal layout from the memory subsystem point of view, because when you're dereferencing neighboring pointers, you will get neighboring objects. On the other hand, here you see non-optimal layout. Why is it non-optimal? So again, here you have a vector of base pointers, but as you see here that the first points to the fifth, the second points to the second, and so on. So they're not pointing to the neighboring, they're pointing to some random places in memory. Now, this non-optimal is, from the hardware point of view, from the memory subsystem point of view, is not good, because you're just targeting random accesses. In the context of memory subsystem, random accesses to memory location is the worst kind of access. Actually, this is where most of the memory bound software can happen. Actually, it can be the difference of 100 times, like speed up of difference of 100 times for very large objects and very fragmented memory. Now, I don't know if you remember when I was like younger, Windows 95 had this problem with memory fragmentation. So when you boot, it would work fast, but as time progresses, it gets slower and slower and slower. This is exactly what happens. So you had more and more random accesses. This is what causes that problem. So how do we solve this? Yes?
So I'm saying this correctly. It's not necessarily an issue with virtual functions, but with representing objects as pointers.
Exactly. So if you have the same problem, if you have the same data representation, you're holding the data in the same way in memory, and you're not calling virtual functions, then you'll get the exactly same problems, exactly the same problem we have. But it is more common to appear in the context of virtual functions and holding pointers to the base objects. Okay. So again, I did the experiment. We have a vector which contains 20 million objects. We have another vector of pointers, and I made it like this: that 20 million objects, and I have 20 million pointers, and neighboring. I create the optimal layout where the neighboring pointer points to the neighboring object. This is the perfect ordering, and I measure how much time I need to iterate through this thing. Now, in the next step, I change a bit. I make the layout a bit worse. I take a certain amount of pointers and exchange their value. So I exchange them so they don't point to neighboring memory. And I'm measuring what is the performance degradation. So, so I shuffle the array, but not a lot, a bit, let's say. And then every time I shuffle the pointer array, I'll see parts of the array and see what happens. And each shuffle where I exchange 2 pointers in the array makes it a bit slower. And it's a cumulative effect. If you do it a little, it doesn't matter. But if you do it a lot, it matters a lot. Okay, so here are the results. So I had 20 million objects, and you see 0, 1, 4, 16, 64, 256K. And you see from 0 to 256K doesn't change a lot. But then as you increase the number of shuffled pointers, it gets really bad. So it gets from about 200 milliseconds to 1,500 milliseconds. So it's a slowdown about 6 times. And it doesn't matter if, so the red one is a non-virtual function and the blue one is a virtual function. But as you can see, it doesn't matter. Slowdown is the same for both. Okay, so you see that the importance of memory layout here. So yes? Maybe I did this experiment maybe more than 1 year ago, but the numbers, let's say the numbers might be different, but the way the graph looks is correct. I don't know, my system had 6 megabytes of L3 cache, and these objects for, I don't remember the size, but let's say 12 bytes per object. It's more than, with 20 million objects, it's more. Yeah, but what you see here is a perfect ordering. Everything's nice. Non-perfect ordering can get really, really bad. Okay, so as I said, the slowdown is not related to virtual functions. It's related to how you store data. And how do we fix it? The question is. Now I have several ways to do it. First one is not to use the first one is not to use vector of pointers. You can use vector of STD variant. With vector of STD variant, you not have this external memory that's allocated. You don't have memory fragmentation, but the size of each object is actually the maximum. So if you have three types, let's say circle, square, rectangle, and rectangle is the biggest, the number of objects will be then the size of rectangle, which is the biggest. So the one item, because STD variant must allocate enough memory to hold the largest object. Another is to use you have instead of having one vector that holds all different type of objects, you can have several vectors. You can have one vector for rectangles, one vector for circles, one vector so on. In that case, that has a lot of advantages. First is you're using the minimal memory. Second is that you are min memory, everything is allocated in the vector, so no waste. You'll see later additional advantages of this approach, but the bad thing about this approach is that you cannot have unsorted. You cannot have rectangle, circle, whatever. So it needs to be unsorted container. The sorting of the container should not matter, because that you're putting everything of this type in one vector and everything of another type in another vector and so on. Now, this approach actually, where they use per vector per type, is used in gaming. And I don't know how many people here work in gaming, because they want high performance for their software, but they don't care about the sorting, ordering, and they're just using that kind of container. Actually, in Boost, you have this Boost base collection that can hold several types of objects, but internally it uses one vector for each type. And this is a good approach if you need it. There's also this thing, polymorphic vector, that I implemented. It's almost some kind of exercise. It's not a production ready, where I take a similar approach to STD variant, array of STD variant, but instead of using STD variant dispatch, which is a bit clunky, I just use the regular vector dispatch. And you can see also source code of this one. Now, questions? Yes? So I created, so instead of allocating this data using new and free, I just took a STD vector and allocated it in an STD vector, and I put the 0th element of this pointer to point to the 0 element of this vector and so on. So it's an exercise. Yes? Oh, sorry, I forgot. So the question was how can I create a optimal layout? So I wasn't using new and delete. I was just using two vectors, one with pointer, one with objects. Okay, let's move on. Next thing about virtual functions is related to compiler optimizations. And what is the catch here? Now, compilers, when do the optimization, one of the most important optimization in compiling is inlining. So what's inlining? Inlining is you have your code calls a certain function, and your function, so what happens is compiler takes that function, copies its body to the place where you made the call. Let's say like this: your call has your place here call to a plus b, to a function that does a plus b. What the compiler with inline does takes a plus b and copies the body of that function to in the place where you call it. Now, why does the compiler do that? One reason why the compiler does it is because to save few instruction calls. So there are few instructions that are related to the call and few instructions that are related to getting back from the function. And this is fine, but this is not the main thing about inlining. The main thing about inlining, because when you inline function, you know more about the function and you can do more optimizations. You can do more optimizations with inlining. So what kind of compiler optimization can the compiler do? So if you have a loop and inside the loop you are calling a function, if there is some expression that is loop invariant, it's constant inside the loop, the compiler can just evaluate it once. It can move it outside of the function and make a smaller loop, and then it will be faster. Also, the compiler can use special instructions to process more than one data at a time in a process called vectorization, and you can typically see improvement of few times, like 2 to 6 times improvement in speed. Now, I have here example. I have this loop here, and it calls function mysqrt. And I have seen, so just a question before getting into the example. What's the problem with the virtual functions? Virtual functions cannot be inlined because you don't know their address. So you cannot inline them. That means you need to call them. That means that many compiler optimizations that the compiler can do, if there were inlining, it cannot do it. Especially if you have a loop that processes different types of objects, you cannot inline this function and that function and that function, so on. Okay, so we have a loop here. And the loop calls this function called mysqrt. And inside this loop, I have something like this. If debug, and a is less than 0, print something on screen, value is negative, and then return std of sqrt of a. Okay. And now the compiler does its magic. It's called loop unswitching. It's a compiler optimization technique. And what it does, it inlines this call here, and it figures out that this debug is essentially doesn't change its value while the loop is executing. Okay. And now what it does, it removes the debug outside of the loop and creates two loops. This is the original loop. Now here we have two loops. The first loop is when the bug is false. So when the bug is false, this nothing here evaluates. Okay. And you have out of e equals std of sqrt of inner d. So it's a really simple loop if the bug is false. But if the bug is true, I see, you see there is no debug here, then we have this std printing to the standard error and calculating sqrt. Now imagine you're running your program, so the compiler has this code here, and the compiler can decide to vectorize this loop only, not this one. It cannot vectorize it because of this print, but it can vectorize this loop. And if you're running with debug equals false, that can be run. It can be executed really fast. But if you're running with debug equals true, then it will be executed slower path, but it will work. Okay, so what I did is experiment. I have here some class called object, and I have this member called m is visible, and I have mid, and I have moffset, and I have these methods is visible, and I have get id 3. Okay, and I have this test loop. So why is this important? Just a second, please. I check inside the loop I did. If the object is visible, which is a call here, then I get count plus equals get id of 3. Okay, and I have get id of 3 mid plus m offset. So mid is some ID here, and m offset is static member. So it's same for all the types. It doesn't change value depending on the type. And what I did is made this function. I made this function is visible and get ID 3. I made it first virtual and then non-virtual. And what happened here? What happened here is that the inline version was 136 milliseconds, and the non-inline version was 242 milliseconds. Now, do you guess why? Can you guess why? Why? Why was the inline version 2 times faster than a non-inline? What happened here? The compiler performed the inlining, but he did some kind of compiler optimization to remove something. Huh? But MID is different for each instance, so it cannot move it. Yeah. What value? M offset, yeah. M offset is same for all. So it loaded it once in a register and kept it in the register all time for the non-virtual call that was inline. Actually, if I remember correctly, in this example, it wasn't about virtual functions. It was regular functions inline versus not inline. Okay. Okay. So, but it's not. Yeah, but each object can have visible or not visible. Okay, so this example, if I remember correctly, it was a long time ago. This example was actually not about virtual functions. It was regular functions inlining versus not inlining. No, the cost is that this M offset, this one, it's the same for all the value. It doesn't change. It's loop invariant. So you can load it once. You don't have to load it every time. Okay. Yes. Yes. So the question is, what about the virtualization? And the answer is exactly. Exactly. So if in the case of devirtualization, if the compiler can devirtualize a call, that makes, because it knows the compile time. It can go to that address immediately. It doesn't have to do this virtual pointer mechanism. Then it can inline it, and it can perform a lot of interesting stuff. But the problem with the virtualization, essentially, if you have a container of random objects, you cannot devirtualize them. The flexibility of virtual functions cannot be changed in any way. It cannot be made better. Yeah, it's a philosophical question, but it's an interesting one. So virtual functions inhibit compiler optimization because they cannot be inlined. And so the solution for this is the same as previous type-based processing, when we have separate vector or separate container per type. In that case, the virtual function mechanism disappears and you don't have problem with inlining. Okay. Now, with regards to compiler optimization, some codes some codes profit more from compiler optimization, some profit less, and actually you don't know that until the compiler does it. So you can, if you have some intuition about compiler optimization, then you can have like, I would expect this loop invariant variable to be moved outside, and I would expect vectorization, but generally you cannot say that. You need just to inline it and see what happens. And actually, if you think about it, you can actually perform inlining you can manually inline even virtual functions if you know the type with ifs. Okay, questions? Okay, let's move on. Jump destination guessing, okay? So what's that? So we have our CPU, it's running our code, and what it does is that modern CPUs, when they execute the code, they're doing it very aggressively. Let's say you have instructions, and certain instructions depend on certain instruction. You have an instruction dependency chain. The compiler will just run in advance, run, and try to fetch as much instruction as possible. Now, what happens is when you have a jump instruction, which calls a jump to certain address, the compiler can start executing before it knows the address. And this is jump destination guessing. It's part of the speculative execution. The topic is really big, and I'm not going to cover it. But just imagine that the compiler can start executing a function before it even knows that this function is needed. It can start executing, and at some point, oh, I'm in the wrong place. What should I do? Let's go back. I'm gonna cancel everything I did until this point and execute the right code. Now this is important for us because virtual functions, there is a jump. If you look at the code, the compiled code, you have a jump instruction to a memory to certain location, and there are like 5 possible locations for 5 types. There are jump to five possible locations, so compiler can guess, aha, I guess this will be jump to this address. Okay, and this is jump destination guessing. Compiler does it all. The CPU does that all the time. Now, if the guess is correct, you actually did something useful. But the guess is wrong, you didn't do anything. You actually need to start over. And this starting over costs time. Now, to show you how it works, I did again experiment. I have 3 vectors, each of 20 million objects. In the first vector, my data is sorted by type. So I have A, B, 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 C, 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 D, 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 D. So I have 4 types. I think I had more in this example. I have 4 types. In the second vector, the data is sorted in a predictable fashion. So round robin, A, B, C, D, A, B, C, D, A, B, C, D. So this is how the types change. And in the third one, the types in vector are just random. So B, C, A, C, D, C, B, A, A, and so on. So we measure the time needed to call a small virtual functions on the 3 types of vectors. So we have the same operation, same virtual function, everything else is same. What is the difference is how the data is sorted in the vector. And what happens is, like, you have sorted by type or sorted in a round robin fashion, it's about less than 200 milliseconds. However, if it's unsorted, the call time is 500 milliseconds. So you guess what's going on. So the reason is that the compiler was guessing, and it managed to guess well here and well in this case, but not in this case. Yes, the CPU, sorry. The CPU was guessing the addresses, and in 2 of those cases, it managed to guess correctly. And in the third one, it didn't manage to guess correctly. Yes? I think I don't think I don't know that if there so if there is any particular reason why they're sorted by type and sorted in round robin fashion.
Then he wasn't able to guess the
To be honestly, I would mostly say that this is the error of measurement. I don't know any hardware reason why this wouldn't be the case. So I wouldn't expect any big difference. But yeah, yes. I don't understand the question. Can you repeat it? Okay. This one doesn't have a lot of cache misses. There was one that had the one when I did this pointer switching. So it was like 10 slides ago. So this one doesn't have a lot of cache misses. I wanted to measure, I made everything same. I had a perfect optimal layer. Everything was perfect because I wanted to measure exactly this. This is what I was guessing at. No, this was pointers and objects, but each pointer points to a neighboring object. Okay? Yes? Okay. It was a speculation problem in the CPU. The CPU was guessing the address of the virtual functions, but it was guessing wrongly. It guessed branch misprediction or jump destination misprediction. Sorry? I think branch misprediction, but I think so. This is not the question is a bit. I don't know exactly. I know there are branch misprediction counters. I haven't seen jump misprediction counters. Maybe there are some, but I would look at the branch misprediction counters. Okay. Okay, moving on. So if you have predictable manner sorted everything, then it will work fine. If not, you will guess strongly. And this problem mostly applies to small virtual functions, not large ones, because with the large virtual functions, you have the price of the call is the length of the function is actually where the most of the time is spent, not on the call itself. Okay. Again, the solution for this type-based processing. So you have a per type vector. Okay. Next, I call instruction cache evictions. Why did I do this? Okay. So when modern CPU executes your code, and it relies on how to say getting intimate with your code, with your instructions. And the code that it has recently executed, it's called hot code. And the code that it hasn't executed recently, it's called the cold code. Now, the CPU for hot code knows some things. It knows the results of branch predictions. It knows the results. Everything is in cache. That's for hot code. But for cold code, it doesn't know these things. And executing hot code is actually faster than executing cold code. What's the problem here? So the amount of code that is hot is limited. And at some point, if the CPU hasn't executed a certain piece of code for a longer time, this code becomes colder and colder, and eventually it gets removed from all the caches and it gets cold. So ideally, when you're executing your code, you want to execute the same code over and over and over. Now, virtual functions, and especially large virtual functions, where each object has a different virtual function, means that we are switching from one implementation. We're executing function A, then we're executing function B, then function C, D, and so on. And each time when it's moving from A to B to C to D, it's actually executing cold code, not hot code. And what happens if you were executing function A 1 million times, function A first 2 times would be cold, but on the third and fourth times it will be hot, and from that point on it will be hot. And with virtual functions and large virtual functions, especially when you're switching between a different implementation, you can get to the point when you're constantly executing cold code. And I have experiment again here. This was the most difficult to measure because it depends on many factors. So it depends on how many different. So if you have a base class, it's not the same if you have 3 derived classes or 30 derived classes or 300 derived classes. So the bigger the number, the slower the code. Again, next thing is the size of the virtual functions. Now, when you say size, it can mean 2 things. It can mean how many instructions there are in the function, or it can mean how, if you count, like I look in the compiler output, okay, this function has 300 instructions, but this is not what I mean under size. I mean how many executed instructions. So if there is a loop in the virtual function, this counts as a slope, as a big function. Now the size, okay. So, and the last thing is how sorted are the objects in the container. Again, we have this problem of sorting. So if they're all sorted by type, or they're random, or they're something else. Now the best case performance-wise when they're sorted by type. So we have A, B, 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 C, 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 D, 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 and so on. The worst case is when you have what? What?
Mixed.
Round robin. A, B, C, D, A, B, C, D, A, B, C, D. You essentially always, the one that comes next is the executed furthest in the history. Okay. And I did an experiment. I have 4 classes, rectangle, circle, line, and monster, and 4 implementation of long virtual function. The long virtual function consists of a for loop with a large if, else, if, else, if, else, if, else block inside it. And again, we use we use a vector of 20 million objects. The first one is sorted by type, the second one robin round. And I changed the size of the functions by changing the number of this if, else, if, else, if, else. So if I have small, like 2 or 3 if, else, if, or I have 20, or we have 300 if, else, if. And then I compare the time they needed to iterate the 2 vectors. Now, this is a relative performance difference between the sorted and round robin vector. So I divided one by another. And runtime sorted divided by the runtime round robin. And this is the number of if-else clauses. I go from 0 to 100. And you see when the number is small, when the function is small, it doesn't matter. But as I increase the number of if-else clauses, it gets down it's about 0.6. In the worst case, the same function took 7.5 seconds to execute in the sorted vector and 12.3 seconds to execute in the round robin vector. So this is the worst case of 40 if-else. So this is for the large loops. Okay. Again, this thing is not related to virtual functions themselves. If you were calling n functions, whatever functions, function A, B, C, D, E, F, G, you will have the same problem. But with virtual functions, it can happen there is much bigger chance that it happens, and much bigger chance that it happens that you didn't plan for it to happen. Yeah.
Can we go back?
Yes.
Why does it increase after 4? It's because it's actually missing in the sorted. It also starts to like.
I don't know.
Lose track of the prediction.
I don't know. I think there are other things here that are also at play. Effects of hardware, effects of compiler, and so on. I don't know why it happens. So I saw that at 40. Yes, that's a good question, but figuring out why it happens, I'm not even sure if it's possible. That's a good thing. Okay, so conclusion is the virtual functions themselves do not incur a lot of things. The problem is the environment they run at. So what hardware wants is what the predictability. They want same type, same function, neighboring virtual address. And with virtual functions, you can create an environment. We have different type, different function, different virtual, different address. So if you have predictability, hardware runs the best. If you don't have it, it runs the slowest. And this thing is difficult to achieve if you're just using virtual function randomly without understanding how this works in hardware. I hope this lecture was a good introduction to the topic. Now, in game development, they use another paradigm instead of OOP. It's called data-oriented design. And the thing is, one of its major parts is this type-based processing that I mentioned several times, where each vector holds one type only. And it eliminates all the problems we see with virtual functions. However, or unfortunately, this approach is not applicable everywhere. So it's only applicable in their domain because they don't need sorted vectors. If you have a domain where you need sorted vectors and you need the flexibility of virtual functions, then you need to pay the price. Okay, so if you want to use virtual functions and you want to use them efficiently, you need to bear a few things in mind. You need to avoid a vector of points around your hot path. Hot path is the thing that it takes the most time. In this way you will avoid data cache misses. Now, data cache misses are things that most cost with regards to software performance. Other factors also play their role, but not that much. With careful design, you can actually reap a lot of benefit with virtual functions without paying the price of just going really, really bad. So how to code fix your code with virtual functions. Bear in mind that arrangement of objects in memory is very important. Try to make small functions non-virtual. So this is also possible. And try to keep the vectors sorted by type. This is not always possible, but yeah. And that's it. Questions? Questions? Well, thank you very much for coming. Hope you enjoyed it and have a good evening. We'll stay here, chat, and later we will go have some drinks. So feel free to stay.